Okay, so we're going to continue with just a few more notes for the lecture from yesterday. And we wanted to do this theorem here. We want to prove this theorem, which says that the complement of a closed set is open. So recall that on yesterday in class, what we proved was, so let me put here, recall, we proved that if S is, let me, let me look at my notes here. We proved that if S is open, then S complement is closed. So S open implies S complement is closed. And now we're proving that the complement of a closed set is open. How do we write this, or how do we go about proving it? Well, assume we have a metric space, M, with the metric D, and let S be a closed set in M. And we want to show, or we claim, that S complement is open. Now, over here on the side, as a refresher, I've written down the definition of some key terms. So, what does it mean for a set to be open in M? What does it mean for a set to be closed in M? And what does it mean for a sequence to converge in M? Okay. So, since we want to prove that S complement is open, we need to show that, or one way to prove that S complement is open is to show that for every point in S complement, there's some distance r greater than 0 where that r ball is contained in the complement. Okay, so if we were to sketch a picture, here's M, and suppose here's S. If S is this subset here, now S complement is all of the points in M that aren't in S, right? So this is S complement. And we want to show that S complement is open. So we want to show that for every point P in S complement, there exists an R. So there exists some R greater than 0 such that the R ball centered at P is contained in S complement. Okay, so one way we could do that would be proof by contradiction. So we'll say, suppose not. Suppose S complement is not open. Then S complement is not open. So what does this mean? We need to negate that definition here for open. So that means that there exists a point P in S complement such that for all R greater than 0, it is not the case that the R ball centered at P is contained in S complement. Now, another way of saying that it's not the case that the R ball centered at P is contained in S complement is to say that that R ball intersected with S is non-empty. Okay, so i.e., there exists a P and S complement such that for all R greater than 0, MR of P intersect S is non-empty. In particular, when R is equal to 1 over N, there will be a point, we could call it Q sub N, which is in both S and that R ball. So there exists P and SC such that for each N in the natural numbers, and we kind of use this argument in class Thursday, so this should not be entirely new. So for each N, there exists Q sub N in S such that the distance between Q sub N and P is less than 1 over N. So now, and we showed this in class, this means, so Q sub N is a sequence in S which converges to P. Now, since S is closed, because this is our main hypothesis, is that S is closed. So since S is closed in M, S contains its limit points. Since P has a sequence, let's highlight this. Just want to highlight it. Right, so back here when we noted that there's a sequence in S which converges to P, that means P is a limit point of S, or P is in the limit of S, right? So P belonging to the limit set of S implies that P belongs to S. We get a contradiction since P belongs to S complement, right? Because we started off with up here, there exists a point in S complement, right? So it must be that S complement is open. Now, good practice, let me write it in different. Okay. So good practice prove that for any P and M and for any R greater than 0, the R ball centered at P is an open set. And also good practice is to prove that for any S that's contained in M, the set of limit points of S is a closed set. So what this means is whenever we have a metric space, we automatically have a huge collection of sets that we know are open, namely R balls that are centered at different points in M. And we have a huge collection of sets that are closed, namely limits, the set of limit points of subsets. Further, since we now know that the complement of an open set is closed and the complement of a closed set is open, we know that the complement of any R ball is closed, right? So we've got even more closed sets, and the complement of set of limit points is going to be open set. So that's just very handy. So let's look here. Note, for any S, right? So for any subset of M, so M is any generic metric space. For any subset of M, S is contained in its set of limit points. Now let's look into why this is true. So let me pull this down here. So we'll put here a question. Why? Well, what does it mean? What is the set, right? What does it mean for a point to be a limit of S? P is a limit of S if and only if there exists a sequence in S which converges to P, right? So if P belongs to S, that means that we could consider the constant sequence P, 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 right? So there exists a sequence, namely the constant sequence of P, 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 dot, 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 right? In S, which converges to P. And this implies that P is a limit of S. So we get this, which is we get this conclusion that S is a subset of the limit points of S. This means that closed sets can be defined by sets that are equal to their set of limit points, right? Because remember, S is closed if and only if it contains its limits, right? So the only way that S is going to be equal to its set of limits is if it contains its limits, right? So that's going to happen when S is closed. Okay, so here's another note. Notice that for any metric space, the empty set is closed and the empty set is open. So in other words, the empty set is always clopin regardless of the metric that you're using. If you're using the discrete metric or some crazy metric, who knows where you got it from, empty set is always going to be closed and open. Now let's look and see why that's true, going back to these definitions that we have written down here. What does it mean for a set to be open? If and only if for all P. So now think about this. If we let S equal the empty set, then this definition is satisfied, is vacuously true, right? And now what about, is the empty set closed? So now in order to be closed, that means for all points P, there's a sequence in the empty set that converges to P. You said, wait a minute, how does that make sense? What if we use our theorem that says if S is open, then the complement is closed, right? So if we show that M is open, that will imply that S is closed. Does that make sense? So if our goal is to show that the empty set is closed, all we have to do is show that M, which is the complement of the empty set, is open. Now, why is M going to be open? M is going to be open because if we let S equal M, it is true that for every point in M, the R ball, any R ball, in fact, centered at that point is going to be contained in M. Because every R ball is a subset of M, right? Okay. So we get that S is open and S is closed because M is open. So the empty set is always clopin. But guess what else we have? Since the empty set is closed, that means M is open. And since the empty set is open, that implies M is closed. So M is also clopin. So M and the empty set are both clopin always. Now if you recall, we talked a little bit about in the very beginning about topological spaces, and within topology, metric spaces are studied, and that's what we've been discussing. And I want to now show the link between metric spaces and topological spaces. So we'll call tau, this is script, right? Script T, tau, let that be the collection of all open sets in M. Okay? Here we have a theorem. First, we're saying that the empty set belongs to tau. In other words, the empty set is open and the entire space is open. So that's part of the theorem. That's number one. And what we're saying is that it doesn't matter the metric, right? The metric is irrelevant. We will always have these three properties satisfied. Okay, number two says that the union, any union of open sets is open. Because remember, script tau is a collection of all open sets. So here we're saying that the union of open sets is, again, an open set. And then number three says that the finite intersection of open sets is open. So anytime you have a finite intersection of open sets, the result is an open set. Now, let's see here. We'll do just a sketch, I think, of maybe one or, we already have covered two, so we know why two is true. I mean, number one. But let's look and see for three. You might be asking yourself, why can't we say, let me add a page below. So a natural question would be, why isn't it, and it is, why isn't it true that for any collection of U sub alpha, the intersection of U sub alpha is open, right? So why must you restrict yourself to finite intersections? And the answer we can give in the form of an example. Consider. Now I'm going to give you my metric space. M is R. My D is just absolute value, right? So D, the Euclidean distance. And I can think of, and in fact, this was in our very first homework set, I think. Our very first homework set, come up with a collection of open intervals whose intersection is a singleton. And so we could come up with, so let U sub n equal, this is for each n and n, U sub n to equal minus 1 over n to 1 over n. So then, for each n, U sub n is open, so it belongs to our set of all open sets, but the intersection of the U sub n's is just going to be the point, the singleton 0, and 0, this singleton is not open. Okay? And why is it not open? Because for any r greater than 0, the r ball centered at 0 is not going to be a subset of this singleton. Okay? So, infinite unions are fine. Countable unions, uncountable unions, again, you'll always end up, if you're taking the union of any open set, any open collection of open sets, the result will be an open set. However, if you're taking intersections of open sets, you're only guaranteed to have the intersection of those open sets be open if there are only finitely many of them. Okay. So let's look at a sketch of number 2. So number 2, or property number 2, says that the union of open sets is open. Okay. So now how would we prove this? So again, the way to think about this is the union, any union of open sets is open. Okay, so hypothesis, we start off with a metric space. This is very reasonable. And script tau is subsets of M, which are open, right? So are you all familiar with this notation here? So this refers to the power set. So this is a set of all subsets of M. Okay. So we want the subsets of M that are open. That's our script. That's our tau. And we have some arbitrary union of open sets. That's the setup. The claim is that now I'm introducing this notation. I'm going to call the union U. And I want to say that U, which is the union, is also open. Proof. Now, what does it mean for U to be open? U is open if and only if for every P in U, there exists an R greater than 0 such that MRP is contained in U, right? So what would we do? So here's the idea. So imagine we've got all these U's, and uncountably many, right? So we've got all these U's, like this is U alpha, this is U beta, right? U gamma, who knows what. Now, P belongs to U if and only if there exists an alpha such that P belongs to U alpha, because U is the union of all these U alphas. So we could zoom in, and we've got some U alpha, which is an open set. Here's a key. Since U alpha is open, that means that there exists an R greater than 0 such that the R ball centered at P is contained in that U alpha, since U alpha is open, right? But now, all we have to do is say that that R ball, being a subset of U alpha, is also going to be a subset of U, because U alpha belongs to the union, or is a subset of the union, right, of all of the U alphas. There's a horrible notation there, so let me not do that. Right, so since U alpha is a subset of the union, and the R ball is contained in U alpha, that R ball is going to be contained in the union as well. So it totally makes sense. Right? If the R ball is contained in one of the U alphas, then it's certainly contained in the union of the U alphas. And that's just a sketch to show why the union of open sets is open. Now, tau is called the topology. So that is what the tau stands for. So tau stands for the topology of open sets of M. Now, you can start off with any set. So for any set X, take a subset of the power set of X, which satisfies 1, 2, and 3. Here's the 1, the 2, and the 3. So if the empty set, so you need the empty set to belong to tau, you need the full set to belong to tau. Unions of members of tau belong to tau. And then lastly, finite intersections of members of tau belong to tau. So that's 3, 2, both of those comprise 1. Anytime you have a subset of the power set that satisfies this, then you now have a topological space. Again, X, comma, script tau for your topological space. Open sets of X are the elements of tau. Okay? So for what we've done for our metric space is we've said if you have, let me choose a darker color. So we've said that for a metric space, let script tau equal, so let's see, what is script tau? What is our collection of open sets? It's going to be the collection of R balls centered at points in M, such that P belongs to M and R is bigger than 0. So then M tau is a topological space. Okay? And the last thing I want to do is I want to talk about how some topologies don't arise from metrics. So in other words, here we see if you have a metric, you can generate a topological space. Remember, this goes back to that whole picture of inside topological spaces, we have metric spaces, right? So every metric gives rise to a topological space. However, some topological spaces do not come from metrics. Let's give an example here. Very simple. Here's our set. Our set is just contains 3 points, A, B, and C. And we have our topology. So this is our set of, so this is all open sets. All open sets. Sets in X. Now, let's quickly verify that tau satisfies 1, 2, and 3. Now, 1, remember, was that it contains the empty set and all of X. Contains the empty set in X. 2, it contains unions, right? So any union, the empty set unioned with any set is that set, so we don't need to check that, right? If I look at AB union with B, I'm just going to get AB, so we're good. AB union with BC, and I get X. AB union with X, again, I don't need to check against X because X union with anything is just going to be X, right? So 2 of these, if I choose any 2 of the middle ones, B union with BC, we didn't do that. B union with BC is just going to be BC. So we're good there. And then if I take the union of all 3 of these proper subsets, AB union B union BC, I just get X. So unions were good. And now what about finite intersections? Well, here we only have finitely many elements of tau, so we can only take finite intersections, right? But just for the sake of argument, if we intersect anything with the empty set, we'll get the empty set. If we intersect anything with X, we'll get that set again. So we're good with those. If we intersect any 2 of these, right, these 2, intersection will just be the singleton B. Intersection will be the singleton B. If we intersect these 2, we'll get B. If we intersect 1, 2, and 3, we'll get B, and we should be good. Okay, so we've just, we could write out by hand, but all of the finite intersections are, again, elements in tau. So X, this does form a topology. We have a topology. These open sets operate the way they should. But the key is here, we're saying tau is not the result of a metric. Now, how do we show that tau is not the result of a metric? Well, let's look at this. Now, if we just consider the point A, and suppose there does exist a metric D such that X tau arises from X with this metric D. Let's just suppose that's true. Then consider A. Now, just by the definition of a metric, we must have that the distance between A and A is equal to 0, right? We've got to have that. The distance between A and B cannot be equal to 0 because A is not equal to B, okay? And the distance between A and C also has got to be strictly positive. So here's the deal, though. Let R equal half of the minimum between the distance between A and B and the distance between A and C. In other words, if here's A, here's B, and here's C, I want to choose R. I just said 1/2, but I want R to be so small that I'm guaranteed to have the R ball centered at A be equal to just a singleton. So this open, it's got to be an open set, because if you have a metric, then all of your R balls are open sets. However, the singleton does not show up in tau. So it is missing. So this topology cannot be the result of an open, cannot be the result of a metric. Okay. Yeah, I think that's it. That's it.